Alright guys, welcome to my virtual classroom. I know this is not ideal, and again, I apologize. However, hopefully you'll get something out of this. Okay, so let's utilize our time together. Make sure you are behaving for the sub. I don't want to have to take away respect points. Alright, so we've been talking about parent functions, right? We talked about, I think most of our classes got through 6, one of the classes got through 7. So I'm going to talk about the 7th one starting out. So if, I think it was 3rd hour, got through the rational function. If you're in 3rd hour, you can fast forward through the rational function explanation and get immediately to the next one so that you can do that. So jumping right in, again, we're going back and we're talking about the names of them, the equations for them, the graph for them, and then the intercepts again to finish up the last two that we did not cover in class today. Okay, so first of all, rational is the next one. The 7th parent function is rational. All right? And rational numbers are anything that can be expressed as a fraction. That's the mathematical definition of a rational number. Okay, so our equation for a rational equation, a rational function, is just f of x equals 1 over x. Okay? Pretty simple. It's basically the inverse of the linear function. Now let's go back to our calculator to see what that looks like. So again, we're going to go back. Got our handy-dandy calculator. If you need to grab one, go ahead and grab one. Go to y equals. Now there's another workaround. Remember when we did the absolute value, we were able to use the alpha and then the window button. For the fractions, you can either do 1 divided by x under your y equals. So you can just do 1 divided by x, and that works. But there's another equation, another workaround, where you can actually hit the alpha y equals button, and you'll see we have another pop-up. And you see this little n over d right here. If you hit that, it gives you a little fraction, okay? So then I can put 1 in the numerator and go down to the denominator and hit x, and it'll look like that. Okay? So if I graph both of these, it actually gives me the same graph in blue, and then it'll go over the same graph again in red. So you can enter it either way. It does not matter. Does not change the graph at all. So as you saw, and as you can see on your calculator, the graph of the rational function looks like this. And again, we put our arrows on there, just like normal, because it does extend all the way, which just makes sense, because as x gets bigger, y is going to get smaller, because 1 over 2 is going to be bigger than 1 over 100, right? Because you got 1/2 and then 1/100th. So as the values get larger to the negative and larger to the positive, it gets closer to 0. However, this is not a thing. We cannot divide by 0. So this line right here, this graph, none of these graphs are ever going to touch the axes. Okay? It's never going to touch this, because we can never have 0 in the numerator because we have 1 in the numerator. We can get really close to it because we can get really big numbers or really small numbers there. However, it's never actually going to touch 0. Okay? So this is one of the exceptions for our intercepts. Okay? Because you can see it never actually intercepts any of the axes. So that means the intercepts for the rational function is no solution. There is no intercept for the parent function, because it gets really close to 0, but it never touches 0 because of this rule, because we cannot divide by 0. Also, it's never going to touch these because we can never get to 0 with our y, because we always have a 1 in the numerator. If this were 0 over x, then it would touch it. However, since it's 1 over x, it's never actually going to be 0. Okay? It'll get really close. So that's the rational function. And again, if you have any questions, message me on Oasis. Send me an email. I don't understand this, Coach Abel, and I'll get back with you as quickly as I can. But I'll be here Wednesday to answer any of your questions and such. Where did my, oh, there's my eraser. All right, so that's the rational function. I'm going to try to make this as quick as possible so that you're not having to struggle through watching a 45-minute video in a 50-minute class. I wouldn't want to do that to you. So the last function that we're going to talk about in here is called the exponential function. Okay? And obviously, by the name, it's going to have an exponent. Okay? So, f of x, the equation for an exponential is f of x equals a to the x power, where our variable is going to be power. Now, this is kind of like the constant. Okay? The graph is going to look different depending on what number we plug in here. Okay? Now, there are some variations on this. I can't put 1 here because then 1 to any power is still going to be 1, so then I may as well just have the constant function of f of x equals 1. So with the exponential function, the only issue is the base cannot be 1. Okay? And usually, as a parent function when we're graphing, we're talking about a whole number, so we don't want it to be a fraction because that would make things wonky. Okay? So the base is going to be a whole number in our exponential fraction. Okay? So let's take a look at the graph. Going back to our graph, we'll go back to y equals, and we'll clear out both of the fractions that I just had. I got back to a clear y equals screen, just like this. Whoop. All right? So now, I'm going to do, let's do, as an example, again, just like the constant function, I'm going to do 2, and then we hit the caret button, to the x power, just like that. Okay? And then I'm going to hit enter. I always hit enter just to be safe so that it enters in that, and then I hit my graph just so nothing wonky happens. And then this should be the graph that you end up getting. Now you can see this is another one where this is the only one where it has an intercept, but the intercept is not going to be the origin. Okay? And we'll talk about why that is here in a second. So the graph for this, it approaches the x-axis right here, so it's really close here, and then it kind of does this number. Okay? And there's actually an arrow on that side. So that's the exponential function graph. Okay? And the reason for that is whenever we have 2 to the 1/2 or 2 to the negative power, going back to Algebra 1 rules, if I have 2 to the negative 1 power, when I have negative exponents, that literally is the same thing as saying 1 over 2 to the first power. Anytime I have a negative exponent, it just means that exponent is the same positively in the denominator. Okay, and I'll explain that a little more whenever I get back to class. I don't have time today. Okay, but the reason for that is an algebraic reason. Okay, so if 2 to the negative 1 power is 1/2, that's why 2 to the negative 1 power here is less than 1. Okay, and the greater the power, so if I have 2 to the negative 4th, that means it's 1 over 2 to the 4th is the actual number, which 2 to the 4th power is actually 16. So that's 1/16. So when I get over here, when x is negative 4, y is 1/16. That's why it gets really, really close to 0. But again, it's not going to actually be 0 over here. It's just going to get smaller and smaller and smaller. Okay? So this is the graph. Now, the intercept right here. The intercept for the exponential parent function is always, no matter what the a is always going to be 0, 1. So you're like, what? Why? All of the others are 0, 0. Why is it changing now? Well, the reason for that is, what's any number, and we'll just go ahead and say a, any number to the 0 power? Well, you learned in Algebra 1 that anything to the 0 power is always 1. So if I plug in 0 for x, it's always going to kick out a 1 for my y. So for the parent function, whenever the exponential function is in its base form, the intercept is always going to be 0, 1. Okay? And it's never going to touch the x-axis. All right? So that is the 2 parent functions that we had not covered in class. So now we should have the names, the equations, the intercepts, and the graphs of all of our functions, parent functions, on our parent function sheet. So the next thing we need to talk about is going to be domain and range. Okay, so we're going to have to revisit some of the characteristics of our functions in order to determine what the domain and range is. But first, we need to understand what domain and range is, basically. Okay? And there's a real simple way to remember this. Okay? Domain. Domain is where I live. I'm kind of a messy guy. I know the classroom is fairly clean right now. It will not stay this clean the entire year, I promise. It will get cluttered. I work better when there is a little bit of clutter around. Things will get left out, that kind of stuff. So my house is usually pretty cluttered. I got dirty. My wife gets on to me all the time for having my dirty laundry not in the basket but in the floor or by my recliner or just wherever it happens to land. So I spread out. I'm one of those people that like to spread things out. Okay? And that's how I remember what domain is. Okay, so domain is all of the x values that our function covers. Okay, so let's take a simple example. Let's do our linear function. Okay, so if I do that, remember my graph is just like this, and it goes on forever and ever and ever, right? These arrows mean I'm going forever and ever. So my x values, remember, are my left and right? This is my x-axis, this is my x-axis, and this is my y-axis, right? So my domain is going to be all of the values that could possibly be used for my graph. So what's the smallest x value that I could have for the linear equation? Well, obviously, it keeps on going forever, so the smallest is going to be negative infinity because it just keeps on going forever and ever and ever into infinity. Okay? So the domain of the linear function goes from, actually it should be dots, not equals. So it goes from negative infinity, and what's the biggest x value I can have on this graph? Well, not only does it keep going to the left, it keeps going to the right as well. So I go from negative infinity to infinity. Now, when I get back, probably on Thursday, we will talk about 3 different ways that we can write domain and range. This is what's called set notation. Okay? It's just because we use parentheses and it's a set. You write the smallest and then you write the largest x value. And it's really kind of the easiest way to understand it, I think. So you just go from the smallest to the largest for your domain. Okay? So my domain for the linear function is going to be negative infinity to infinity. So you can write that. D colon, parentheses, negative infinity, comma, infinity, close parentheses for your domain for the linear function, which is your second sheet on the worksheet. Okay? Now, range. In a very similar way, my range is all of my y values of my function. Now, the way I remember this is I'm a hunter. I love to go duck hunting. Okay? So if there's a duck that's really close to me, I usually aim my gun right at the duck. However, if the duck has some distance between me and it, I actually have to raise my gun slightly above the duck in order for the shot to get far enough to get to the duck. So I remember that by thinking, okay, range, I have to raise my gun up and down to change the range of how far my bullets may go. Okay? And that's how I remember range is all of my y values, because the y-axis is what goes up and down. Okay? So range is all of my y values, or my up and down values. So how far down does the linear function go? Well, it goes down and keeps going down and keeps going down and keeps going down to negative infinity. So my range, in the same way, I had d colon, I can write r colon, negative infinity, and then in the same way, it keeps going up as well as x is getting bigger. So my range of my linear function is also negative infinity to infinity. Okay? Now, there are some of the functions that are going to have different ranges. This is the simple one. Okay? It's just negative infinity to infinity on our domain and negative infinity to infinity on our range. Okay? Pretty straightforward. But let's take into account our first one, our constant. Our constant function with the domain and range. Remember, our graph was just a horizontal line, right? For our constant function. All right, so that means with the constant function, my domain is going to be the same as my linear function because my domain, remember, is my left and my right. I spread my chunk out at my home, my domain, where I live, okay? So my domain, again, is going to be negative infinity to infinity. Because from to the left to the right, I go on forever and ever. All right? However, my range is different. How far up and down does my range go? And remember, just a reminder, our equation is f of x equals a for our constant function. Okay? So if this is the case, my range is simply going to be a. Because this graph never goes up and never goes down from a. It's always a. The y value, my range is all of my smallest to my largest y values. Well, there is no smallest and there is no largest because there's only one y value for this entire function. And it's just going to be a. Okay? So my domain of my constant function is negative infinity to infinity. My range is simply a. That's the only y value that I'm going to have for my constant function. All right? So let's look at another different example. Let's just move right on down. Let's go to the quadratic function. And remember, quadratic, my equation was f of x equals x squared. And then my graph. The easiest way to tell what my domain and range is going to be is from my graph. I didn't draw that very well because it's supposed to go through the origin, but you get the idea. Okay, so this is my quadratic equation. So again, my domain, it keeps going. Now, it goes up pretty steadily, but it never stops. It continues to grow this way into infinity. Okay, so again, my domain for my quadratic formula, or not my quadratic formula, my quadratic function, parent function, is going to be negative infinity to infinity. Because from the left to the right, this graph keeps going in both directions. Just keeps getting bigger and bigger. However, range is a little different. It's not just a like the constant function is, and it's not negative infinity to infinity like the linear function was. But look at it. What is it? Well, what's the smallest y value that is covered in the quadratic equation? Well, the smallest would be the lowest, the furthest it gets down, which would be right here. Right? That's the smallest. It comes from infinity, comes all the way down here to the vertex, or the intercept, the origin 0, 0, and then it turns and goes back up. So the range for the quadratic function would be 0 to infinity. Okay? Now, that does not take into account. We're going to talk about in behavior, which is a little different. It's similar to domain and range, but it's a little different. Okay? So we'll talk about that tomorrow. But our range for a quadratic function is 0 to infinity because 0 is the lowest y value. Domain is negative infinity to infinity because it stretches out forever to the left and to the right. All right? Now, the square root function. This is a fun one to do domain and range. Square root function. Now remember, the equation for the square root function was simply f of x equals the square root of x. Right? So now, what do we look at? Well, let's look at the graph. Now remember, this was the inverse function of the quadratic, but we only have the top half, so it just kind of goes like this. And that would be the square root function. So, thinking back to the definition of domain, it's my smallest x value to my largest x value. So what is the smallest x value I could possibly have for my square root? It's going to be 0, because I don't have any part of my graph that's to the left of the y-axis. So my domain for my square root parent function starts at 0, and then it extends on into infinity, because we have an arrow going that way. Okay? So we go from 0 to infinity. Now this is one that's a little bit strange. With our range, the lower bound is pretty easy to identify, because we can see it doesn't go below the x-axis. So the lower bound obviously is 0. However, the upper bound is a little tougher because the graph is kind of misleading. It looks like it kind of tapers off here at a value and just stops. However, thinking mathematically, if this number is 587 million, then the square root of that is going to be somewhere a pretty big number that's going to be off of this. So the range actually keeps going up. It just goes up much more gradually than the domain does. Okay? However, if we were to plug in infinity into the square root function, it would give us infinity. I know it doesn't make sense. Square root of infinity is infinity. That's a whole other conversation that we'll have some other time. However, this is the domain and range that I want you to write down on your sheets for the parent function of the square root. Okay? So, domain of the square root function is 0 to infinity, and the range of the square root function is also 0 to infinity. Keeps everything in the first quadrant. All right? Everything good? All right. So now, we've got the front page with the domain and the range of all of the functions. So now let's flip our page over and go to the cubic. Cubic function, which again, the equation is f of x equals x cubed. Right? So, the graph. And if you need, you can enter these back in the calculator so that you can remind yourself of the graph. You should have them written on your page as well. But some of you, I saw some of your graphs were really, really a little wonky. So if you need a refresher on what it actually looks like, you can always use the calculator to graph it again. But it looks something like this. Okay? So, the domain. Again, this one is a little misleading because it kind of looks like it goes straight down and stops expanding. However, it doesn't, because there is no x value that I can't plug into here. I can plug in negative 563 and then multiply negative 563 times negative 563 times negative 563, and I'm still going to get an answer. It's going to be a really, really big answer down here because it's going to be negative because I have 3 negatives cubed. However, that's why the graph extends down so steeply, is because I'm cubing it. So the numbers, as the x values get larger, the answers get larger quicker, okay? So while it looks like it doesn't expand into infinity, it actually indeed does. So the domain of the cubic function is from infinity to, negative infinity to infinity. Remember, negative infinity is the smallest x. Infinity is going to be the largest x. And the same for the range. The range for this is also going to be negative infinity to infinity. Because obviously, it's going to keep going down and keep going up. Okay? Clear as mud, I know. We're almost done, I promise. All right. Next one, the absolute value. Pretty straightforward. We talked about this at length in most of the classes yesterday. Absolute value. And again, the equation for that is f of x equals the absolute value of x. And this is our graph that we have the flying V. So it comes down the origin and comes back up. And we do have arrows. So now, remembering what the arrows mean, our domain, smallest x, it keeps going this way. So our smallest x is going to be negative infinity. And our largest x, it keeps on going into infinity as well, is also going to be infinity. And some of you guys may have to practice writing the infinity signs. They're just 8s on their sides, but they take a little practice getting used to. I still don't write them really well, so you're going to use this a lot in domain and range in the first several weeks in Algebra 2, so I would suggest practicing writing them so that they're not wonky on your quizzes and tests. Okay? So, domain is there. Now, range again. Again, this graph looks very similar to the quadratic equation, quadratic function, okay? And the range is exactly the same. Because an absolute value is a distance, is a measure of distance, we can't have that value as a negative. So that means we don't go from negative infinity to infinity because we don't have any negative values in the y's. We do have negative values in the x's because we're going left to right on both sides of the axis. But on the y value, going up and down, we only go from 0 to infinity. So again, domain is the smallest to the largest, x, range is the smallest to the largest in the y's. Okay? So since the smallest y we have is 0, that's where we start at 0 and go to infinity. All right? Now, rationals. Rational function, next to the last one. Rational function, again, we just talked about it at the very beginning of this video. F of x equals 1 over x, correct? Now, this one is a little bit different because we have these values down here, we have these values down here. Now, in set notation, we're supposed to write everything that is a possibility, okay, from smallest to largest. And it looks like we should write the domain as negative infinity to infinity for our domain because it keeps going. Our arrows go this way, and our arrows go that way. So our smallest x would be negative infinity, and also our largest x is also going to be infinity. However, there is a slight difference in this domain and range. Because as I talked about earlier, what values cannot be included in the x? 0 is what you were thinking. I heard that. Thank you. Okay, so you can't divide by 0. So therefore, we cannot have 0 as a part of our domain. Okay, so our domain goes from negative infinity to 0, and then we use a bracket saying that it does not include 0. Okay? The parentheses means we include it. The bracket means we do not. Okay? And then we do the same thing, 0 to infinity for the domain. All right? It does include infinity. It does not include. So basically, using set notation, what I just wrote was the domain goes from negative infinity to 0, but it doesn't touch 0. And then it starts back at 0 without touching it and goes to infinity. Okay, so that is the domain. And for the rational, the range is exactly the same. Negative infinity to 0 with a bracket, and then a bracket 0 to infinity with the parentheses. Clear as mud. We can go over this again tomorrow in class, but I did want to introduce you to that because it is a little different. And this is the mathematical way to write the domain and range here. Okay, so it does not include 0 because you cannot divide by a 0, and the range does not include 0 because I don't have a 0 in the numerator, and so there would be no way the answer would ever be 0 because I can't get there with this function. Okay, and finally, I know you guys are ready to be done watching this video. I apologize for being so long. However, I'm sure you guys are having a better day than me. The last one, the exponential. Exponential function. Okay? Again, the equation for that is f of x equals a to the x. Right? And then our graph was something like this. Now, this is a little bit of a different one for domain and range. With the parent function, because it looks like this, we're assuming that a is going to be a positive number. Okay? So that's a little bit, I didn't say that at the first. I probably should have, but I didn't. So I apologize for that. But we're just going to assume it now, okay? Because it's going up. If we had a negative number, it would start down here and go down. We'll get into that whenever we talk about transformations and translations, okay? So with this graph, assuming that A is positive, our domain, again, goes back to the negative infinity to infinity, okay? Pretty straightforward. There's no x that could be too small. We can have negative exponents, okay? It just means they're fractions and they stay just above. And then we go to infinity, right? Because we can plug in any number we want. We could say 2 to the 9,000, and it's going to be a super huge number, okay? But we can still plug it in, and it's still going to work. All right? So the domain is negative infinity to infinity, and the range is actually going to be, I wrote that wrong, 0 to infinity, with a bracket by the 0. And here's the reason. We're assuming that A is a positive number that's larger than 2. 2 or larger, because 1 doesn't work, because 1 would always be 1. Okay? With that said, there's no way that I can get a number, there's no number small enough or a large enough negative that I can get all the way down to 0. I can get a really, really big fraction. I can have 1 over 1 billion, which would be a really, really small number and really, really close to 0, but there's no number that I can plug into this function that I can actually get all the way down to 0. Okay? So it comes down to 0, but it never actually touches 0 on my range. So that's why I put the bracket by the range. Okay? So, domain is negative infinity to infinity. The range goes down to 0, but it doesn't actually touch 0. So 0 is not included in the range, but it's every number up to 0 that's larger than 0 all the way to infinity. So that's the domain and the range of the parent functions. Go ahead and write those things down. Hopefully this explanation was okay and not too boring. And again, be good for the sub. Hopefully you have time to watch this video and then maybe work together to fill out anything that you may have missed. And again, I appreciate your thoughts and your prayers for Isaac. And I will see you guys bright and early Wednesday. Appreciate you.